the law of cosines?
The law of cosine is c squared equals a squared plus b squared minus 2ab cosine of c.
And always that pattern. In other words, I can put a over here, but then it's b and c cosine of a.
Right.
Okay, so there's really three equations for the law of cosines. So in this particular case, show that AC, okay, well, AC is the side opposite the unknown angle, and we have the two other dimensions. So if I let C be AC, okay, so C squared is going to be A squared, 4 squared, plus 5 squared, minus 2, 4 times 5, times the cosine of the angle opposite this side, which is x. Okay, so now...
Oh, okay. I see where I messed up.
So now, if we start from there and take the square root of both sides, we get the square root of 16 plus 25, that's 41, minus 40 cosine of x, which is what they wanted us to prove that it was equal to.
Yes. Okay, that makes more sense.
Okay. Now, that's kind of an interesting problem because you wouldn't use the law of cosines on that triangle. You would use the law of sines. Because we have an angle and its opposite side, once you have that relationship established, then you could use the law of sines at least to figure out this angle here. And then once I figured out that angle, well, now I know what x is because the three of them have to be equal. I mean, 180. So I would be able to solve this entirely with the law of sines. I wouldn't have to use the law of cosines. Typically, the law of cosines is used in only two situations. That is where you have side-side angle, like that. Where you have side angle side. Notice that if I have side angle side, I do not have a relationship between an angle and its opposite side. In other words, I can't solve this triangle using the law of sines. So therefore, I use the law of cosines to get started on it. I end up having to use the law of sines. You have to use the law of sines at some point in every triangle that you solve. But the two situations where you always start out using the law of cosines are this one and where you have just three sides.
Right.
Those two situations require you to start the problem out using the law of cosines. Once you solve for one other entity, then you finish the problem using the law of sines. So, use the sine rule to come up with another expression for AC. Well, what would that be?
So for a and sine of a, it'd be 4 over the sine of 30.
Okay.
Which would equal b over the sine of x, which would equal 5 over the sine of c.
Okay, when you said b, you meant little b, which is the same as AC, right?
Right.
So I'll fill in that over the sine of x. And so they said come up with another expression for AC. There it is.
Right.
4 sine x over sine 30. And of course this is 1/2. So the final expression is 8 sine x. Since that's 1/2, 8 sine x is equal to AC. And I would imagine they probably want you to get it to that level. Right or not?
Right.
Would this be an acceptable answer?
Um,
So all they said was come up with another expression for it. So
right.
it's tough for me to tell with IB. I never know quite what they're
Right.
looking for. It's like only IB would say use the cosine rule to show what that is, as opposed to use the law of cosines to figure out what AC is.
Right.
Okay, so for C, find x, give your answer to 2 decimal places. Okay, so we didn't solve for AC yet. Yeah, we did. It's AC is that. Well, finding x at this point is relatively easy by using the law of sines and solving for this angle. Well, we don't need to, I guess. Let's see. Our expression for AC is still, in other words, we don't know what x is and we don't know what AC is. So we can't solve for x from that.
Do we combine the two as in?
Well, it's pretty easy to solve for x. Let me show you how I would solve for x using the law of sines. We would, if I'm trying to solve for x, then I'm going to say x, well, first of all, I'm going to solve for this angle here.
No, but you see, though, when IB uses the word hence, it means it wants you to use the previous answer.
Oh, okay. All right. The previous 2 answers, probably, right?
Yes.
All right. So we have.
Would I then set them equal to each other?
Yeah, we do. We have AC equals this from A. And we also have AC equals, what was it, 8 sine of x?
Yes.
Okay, so since they're both AC, I'm going to set that equal to that. So I've got 8 sine x equal square root of 41 minus 40 cosine x. And now we have to solve that. Okay, how do I solve that? Well, they really do make you do this the hard way, because there was a real easy way by solving for that other angle in one quick step.
Yes, that's how I would do it, but they...
Okay.
Yeah, you gotta get my teacher wrote this, so...
How do I solve when I have a radical?
Radical as in the square root?
Yeah, which is what I have here. In other words, I have 8 sine x equals the square root of this other entity. So
square root both sides?
I would square both sides. Okay?
Right.
So now I have 64 sine squared x equals what's inside over here. Now, when you're trying to solve a trig equation, it's very difficult if you have 2 different trig functions in the equation. So you want to try to get everything to one trig function.
Right, and then I use the unit of life, as he calls it, and
use the Pythagorean identity for sine squared to convert this to cosine squared.
Right, so sine squared is the equivalent of 1 minus cosine squared.
Correct. Now I have a quadratic in cosine x.
Yes.
Okay, let's get everything on one, let's distribute, get everything on one side and put 0 on the other. And I'm going to minus 41 plus 40 cosine x equals 0. And now I like having a positive coefficient in front of my term that is squared. So I'm going to divide both sides by -1. So now I've got 64 cosine squared x minus 40 cosine x. This would have been plus 23, now becomes minus 23 equals 0. Now, you see where this is a quadratic in cosine x?
Yes.
Okay. If people have difficulty seeing that, I usually show them the method of substitution, where I would let u equal cosine x, which turns this into 64u squared minus 40u minus 23. We would factor it accordingly and then resubstitute when we're done. But as long as you're comfortable working with quadratics, we don't need to do that.
Yes, I'm comfortable with it.
Okay. Solving this doesn't appear to be the easiest thing in the world. Let's see. There's only two factors of 23, so it's got to be 23 and 1. And if this is 8 and 8, that won't work. Let's see. What are factors of 64? There's 32 and 2. There's 16 and 4. That might work. I would be multiplying the 23 times the 4, which would give me 92. And then the 16 times the 1, no, that doesn't work either. And there's 8 and 8, and that certainly isn't going to work. I'm going to multiply 23 times 8 and be way too big. So let's try the quadratic. In other words, whenever you're trying to solve a quadratic, there's an optimum amount of time you want to spend trying to factor it before you decide that this is not going to factor and I'm going to have to use the quadratic formula. So this might factor and I'm just not seeing it, but let's apply the quadratic formula because it's important to be able to know how to do that with quadratics that are not quadratics in x. So the quadratic formula would say not x equals cosine of x equals minus b plus or minus b squared minus 4ac all over 2a. So what is that?
40 plus or minus negative 40 squared, which would be 1,600 minus 4 times 64 times negative 23.
You have a calculator handy?
Yes, I do.
That's a positive number after you apply the two negative signs. So it'll be 1,600 plus that.
I got 7,488.
Before or after taking the square root?
Before.
Okay, now take the square root of that. What do we get?
86.5.
Okay, an irrational number then. Okay, so what was the, before you took the square root of it?
7,488.
So there's our answer. For cosine of x, which answer? Now let's see. When you get a quadratic in trig functions, you almost always end up with two answers, one of which is impossible. Okay?
Right.
I've got the cosine of x being 40 plus that number over 128, and I got the cosine of x as being 40 minus that number over 128. If either of those answers is greater than 1 or less than -1, then that solution is extraneous, invalid, and you only use the other solution.
Right.
What did you get when you took the square root of that? 85 point something?
86.5.
86.5. So when I add that to 40 and divide by 128, I'm less than 1.
Yes.
When I subtract that from 40 and divide by 128, I'm greater than -1. So both of these solutions are going to work. Okay, so here's what we have. What were the instructions? Round this off to 2 decimal places?
Yes.
What's the second decimal place of the square root of 7488?
You see what I normally do so that way I could keep the most accurate result?
Okay, good. So,
have the...
okay, so we want to take the inverse cosine of 40 plus root 7488 all over 128. That'll maintain your accuracy. Come up with an answer for that, which we will round to the nearest hundredth. That's a little tough to put in your calculator, but not really. I mean, you have to be very judicious about your use of parentheses.
Right.
This is one I actually... Are you familiar with Wolfram Alpha?
Yes.
Wolfram Alpha had a beauty... What you use the Inspire or the TI-84 as your normal calculator?
TI-84 Plus.
Okay. Problem with the TI-84 Plus is it does not give you feedback, whereas this does. In other words, if I do this on Wolfram Alpha, it'll tell me if I'm putting it in incorrectly or not, because it shows me what I've put in. So let me put this in here. $74.88.
Wouldn't it be to the 1/2, not squared?
Oh, thank you. 0.5. And then I need another set of parentheses to divide this whole thing by 128. All right, let's see what I put in. In other words, let's see if I put it in correctly. Yeah, that's exactly what I was intending, was to get this. But this is a nice feature that your calculator doesn't do for you. And I've spent all day on my calculator before trying to get the parentheses right and having difficulty. So this is quite helpful. Sorry, what?
Actually, there is a way.
Oh, there's a way to see what it puts in?
No, there's a way to do fractions easier on the TI-84.
Okay.
You do alpha and F1, and it gives you the options for the fractions.
Oh, you mean the fraction of 0.5?
Yes.
The fractional exponent?
No. You click alpha, and then y equals.
Okay.
And it comes up with the option of n over d.
Uh-huh. Oh, I see.
And that's what I use.
Oh, okay. I got you. Yeah. Okay. Yeah, I didn't know that. I used to I have a TI-84. In fact, I have one online. that I think I've showed you before. The one I use in person is the Inspire. And the Inspire is a little bit better because it lets you put in functions in a different mode where you can actually see the exponent going in instead of having to raise stuff to the 0.5 power and stuff. Okay, so this is one answer. So this is 0.15. Now,
which mode are you in? Are you in radian or degree?
Result in radians. So I'm in radians here.
Shouldn't I be in degrees?
Well, yeah, unfortunately with my free version of Wolfram Alpha, I'm not sure. Maybe I can change it to degrees. I'm not sure how. Yeah. But anyway, if you can do this in your calculator, you can put your mode into degrees and come up with this. And then to get the second answer, I'm going to leave it in radians for the moment just because I don't know how to easily, here we go, conversion from radians to degrees. Let's see if it'll let me do that. 8.682 degrees. It gave it to me in both. Okay. Now if I want the other answer, I just change the plus sign to a minus.
Right. Wait, isn't it supposed to be the square root of 7,485?
Maybe I put it in wrong when I did it. What did you get? You were the one that gave me the number. I might have written it down wrong. What was 1,600 plus that?
Hold on.
4 times 4 is 6. 8's got to be the last digit. So I think it's 788.
I wrote it down wrong.
Is it 7488?
Yes.
Okay, cool. So the second answer, and of course they didn't give it to us to the hundredth place. It's funny. They give it to us in radians to 25 different places, and when they give it to us in degrees, they round it off to the nearest tenth. So you might have to do that one on your own.
I got it.
Okay. You got the second digit? We can always take this number and convert it using 180 over pi to come up with that second digit there. All right.
No, I have
it. Okay. So let's see. What else do we have on that page? Wow, that's amazing how much work they make you to go through to learn that method as opposed to doing it the easy way. Yeah, I find that okay. I like that as a way of teaching. All right, find y. By any method we want.
Aren't we supposed to find AC first? Or do we?
Oh, right. We just did C. Yes, we didn't do D. Find AC in proper units. Okay, well that's easy enough. We've got AC was equal to 8 times the sine of x. So now that you have x, you can get AC easily. That line right there at the top, AC is equal to 8 sine x.
Yes, but which x would I use? Just plug in both of them?
Yeah.
I mean, theoretically, 111.32 would make more mathematical sense considering the picture.
Yes. So use that one.
We'll just do that one instead.
Yeah. the reason we get two answers has to do with the fact that this is actually a case of the ambiguous case of the law of sines. If I give you angle side side of 35 and 4, there's not just one triangle that can be made. There's two.
Right.
And the ambiguous case of the law of sines is really the only difficulty when using the law of sines. In other words, let me show you. If I draw this triangle like this, the way they've done it, where that's 30, that's 5, and that's 4, well, I can draw another triangle that still has 30-degree angle there, still has 5, and still has 4. We're dealing with side-side angle, which means that is not a unique triangle. There's a possibility that you could have two solutions. And this is one of those possibilities. Okay? So that other answer we got for x, the very small degree answer, is that angle right there.
Right.
But it's a different triangle. It's not the triangle drawn here. So when we solve this triangle, we know that angle x is the obtuse angle. It's not a small acute angle. So we would use that solution for x. We wouldn't even use both of them.
Right.
Yeah, interesting. I've not seen that before, where they give you a triangle that is the ambiguous case. In other words, if I merely said solve that triangle, there's two solutions. There's this solution and there's also this solution over here. And you'd have to solve all three angles and all three sides for both solutions. When they give it to you in a picture like this, then I don't have to worry about the second one. I can see that that's not the triangle they're talking about.
Right.
Okay. So we know how to get AC.
Right.
Now solving for y. Apparently we can use any technique we want.
Yes.
Well, what kind of triangle do we have? We have a triangle where we know all three sides, and that's the only thing we know.
Right.
We know AC. Now, it's isosceles also. I don't know if that's going to help any. But AC, did we come up with a number for AC?
Yes.
What is it?
7.45.
Okay, well this is the case where you have a triangle where the only thing you know are all three sides. You don't know any angles. And it's true, I can't figure out that angle, or that angle. It means I got to use the law of cosines.
Right.
Okay, so you can pick any angle you want. Let's call that AC, and what's the other one? It's D. So ACD.
Yes.
So let's see. Let's solve. They want us to solve for D. So let's make sure we have cosine of D as the last term in the law of sines. So what's the rest of it going to be?
That would mean that it would be
the side opposite D would go on the left side of the equation. Now we have an equation that only has one variable in it, D. Do you know how to solve for D from this point?
Yes.
Okay. In other words, you're going to end up with cosine of D equals some number. You're going to have to take the inverse cosine of that number. That'll give you D.
Right.
Okay. Well, it looks like we're only going to have time for this page. Let's see that last question. Now find the area of triangle ACD. Well, have you been taught the area of a triangle as a function of the three sides? Heron's formula?
What formula?
It's called Heron's formula or Hero's formula. Either one?
No.
Well, let's see. How are we going to find the area of that triangle? In other words, there's a formula. If you know the three sides of a triangle, you can get the area. If I remember right, it is the area equals the square root of one side squared plus the second side squared plus the third side squared, all divided by 2. I'm going to have to look it up. But if you haven't had that, that may not be the way they want you to solve this.
I do know that whenever they use hence, they want me to use the previous.
Okay, I know how to do it using the previous instead of Heron's. Notice that this triangle is isosceles. Therefore, I can drop a vertical from D. And now I can solve for that vertical by using trig functions. If I know that angle D, we just calculated it from the previous part.
Right.
Okay. So this is half of D. Once you know that, you also know that this side right here is half of 7.45. And you can solve for this altitude, and then you know the base and the height of that triangle, so you'll be able to calculate the area of it. Using area 1/2 base times height. Base is going to be 7.45. Height is going to be whatever this altitude comes out to be.
Actually, in my formula packet, they've given me an equation saying area is 1/2 times A times B times the sine of C.
Oh, okay. Yeah. Well, then you can use that.
Right.
I think you know all the variables, don't you?
Yes.
Okay. Yeah. There's a few area formulas for triangles that are a little easier to use than having to figure out the base and the height. You can't always do that. So if you know some of the angles, you can use that formula that you just said. There's also Hero's formula or Heron's formula. I've seen it both ways in books, with the N after Hero and without the N. All right. Is that going to be good for you for tonight? We need to look at...
Yes.
Yes, that'll be good for you?
Yes.
Okay. Because I can take extra time if you need it. We can...
I think I'll be okay.
Okay. This log, just combine that into a single log expression. And that you're going to end up with log base 3 of 2x.
All right.
Okay. These are composite functions. I think you are good with those, you said, I believe.
Yes.
And, all right. You good to go?
Yep, I'll be good.
Okay, Diana. I will talk to you next Thursday.
All right.
Bye-bye.
Bye.